breakthrough projects. In this video, we are going to explain about the project that is YOLOv8 QSD, an improved small object detection algorithm for autonomous vehicles based on YOLOv8. Before getting into the execution, first let us understand what is the project about. So, when we talk about autonomous driving, there's been a lot of progress recently. The reason behind this is a huge improvements in the technology, especially in things like perception systems and deep learning. With all the new computational power, self driving cars are becoming much better at understanding their surroundings. And then, with sensors like cameras, radars, and LIDARs, that is LIDARs, becoming more affordable, it is becoming easier to equip these cars with all the tools they need to see the world around them. Now, the self driving cars that we have. The self driving cars to actually work safely in the real world, they need to have a really solid perception system. It is not enough for the car to just see other objects. It needs to be able to detect them accurately, figure out what they are doing, and predict what they might do next. And this is all has to happen really fast in real time so that the vehicle can make decisions without hesitation. So this becomes even more important when you're dealing with tricky scenarios where low light, fog, or when the car is speeding down on a highway. It's about making sure that car can see and react to things just as well as human driver would, even when the conditions aren't perfect. Even with the all amazing advancements we have seen in autonomous driving technology, there is still being a challenge that needs to be solved: detecting small objects in the complex environments. So here where YOLO comes into the picture. That is, you only look once. It's a popular object detection algorithm known for its speed and efficiency. It works by scanning the entire image in one go, detecting multiple objects in one pass. This makes it ideal for applications where quick decisions are crucial, like autonomous driving. Here, the algorithms like YOLO V8, that is YOLO version 8, is an advanced version of the YOLO designed to improve the earlier models, while YOLO V8 excels at detecting larger objects like cars or road signs. It has difficulty when it comes to detecting smaller objects such as pedestrians, cycles, or debris. This is a real concern for commercial vehicles, where a larger and more prone to accidents. The challenge arises because small object detection system can't spot these objects in real time. It can lead to dangerous situations. So that's why we need an important that's why we need an improving detection system to handle small objects more effectively while maintaining performance in all traffic conditions. It is so important. So to overcome with all these issues, in this project, YOLO V8 QSD has been proposed, which is designed to work better in detecting small objects in self-driving cars. You see, while YOLO V8, that is You Only Look Once version 8, is already good at detecting things like cars and road signs, but it struggles with small objects, especially in fast-moving, high-speed environments. This network builds on YOLO V8 but makes some part of improvement. So here we have made some advancements to this YOLO V8 where we have introduced structural reparameterization technique. So this helps to make the detection process more efficient by improving the backbone of the model. And now to better identify the small objects, here bidirectional feature pyramid network has been used. That is by FPN. So this allows the model to combine features from different scales, meaning it can capture both the large and small objects more effectively. And the system also introduces a new query based approach. So the project introduces a new query based model with a specialized pipeline structure. This helps in detecting objects that are far away, something that's tricky in driving scenarios, while keeping the processing power low and efficient. All of this makes the model faster and more accurate, which is exactly what commercial vehicles need for safe, high speed driving. And to see how well the YOLO V8 QSD network works, two datasets have been used in this project. That is SODA and Wistron dataset. SODA, it stands for Small Object Detection Dataset for Autonomous Driving. So this dataset focuses on small objects in driving environments like pedestrians or cyclists, which can be difficult to spot, but they are crucial for safety. And the next data set is Viz drone. This comes from aerial object detection, meaning it includes images captured from drones and contains a wide variety of objects seen from different angles in different conditions. So by using both of these data sets, the system can be tested and making sure that it can detect objects accurately and efficiently, whether it is looking for small things on the road or more complex in aerial views. So this is what the proposed system is. And to further improve the performance, here advanced versions of the YOLO are incorporated that are YOLO V5S6, YOLO V5X6, and the newest version that is YOLO V9. These versions are more advanced and gives the system a boost in performance, especially when it comes to the speed and accuracy. This is really helpful when we are dealing with the complex detection which are common in autonomous driving scenarios where quick and precise object detection is crucial. And we have developed a front end of the project. So we have developed application front end application using Flash framework. So this allows users to conduct user testing where users can interact with the system to see how well it works to make sure the system remains secure. And we have added user authentication for that. So only authorized users can access the system for evaluation. And this combination of advanced models and user friendly interface makes it easier to test and improve the overall performance. Moving on to the implementation, to implement this project, we have followed the steps mentioned in the flow of work. So first, we have imported all the required libraries that are OpenCV, NumPy, TensorFlow, and PyTorch for handling the data, that is handling images, data manipulation, and neural network processing. And then comes exploring the data set where before we start working with the model, we explore the data set to understand it, where we load the data set to the project environment so that we can work with it. And then we visualize the image to see what we are dealing with. And then comes image processing when we then process images to prepare for object detection. So here we transform image into a format that the neural network can understand that is called as blob object. Then comes defining the class. This refers to the categories or labels we want to detect in the images. And then comes declaring bounding boxes. So here the areas in the image where objects are detected. A bounding box has been drawn, I mean it is drawn, helps the model to know where to focus on. Converting the array to NumPy array. So here we convert the image into a NumPy array for easier manipulation and processing. Then comes loading pre-trained model. Instead of training a model from scratch, we load already trained YOLO model. So this step involves loading the architecture of the neural network. Extracting the output layers. So the output layers of the network are where the object detection results will come from. And then comes image processing where we perform more image pre-processing to make the images suitable for our model. Here appending the image annotation files and images. So here we associate images with their labels or annotations. And then this step ensures that the image color is in the correct format. So here we convert image from BGR color format to RGB. Then comes creating the mask. So here we create a mask to indicate the areas of the image that are relevant for detection. Coming to resizing the image. So here the model expects images from of a certain size. So we resize the images accordingly. Then comes data augmentation. Here this step adds randomness to the images like changing the order of color that are applying slight distortions. Then comes rotating the image. So here we rotate the image to help the model to learn to detect objects from right angles. Then comes transforming the image. So here we add additional transformations to further enhance the image variety. Processing the data based on YOLO family. So here we pre-process the image data to match the format expected by the YOLO model, which is crucial for accurate detection. And then comes building the model. So here comes the building the model. So here we have prepared everything. So we build YOLO model, including defining layers and settings. Then comes training the model. So here in the step, we use prepare dataset to train the model, teaching it detect objects accurately. Then comes dumping the best model for detecting it in the further. So the best version of the YOLO is has been saved. So the best version of the YOLO, which is performing well, will be saved and used in the future for detecting the small objects. Coming to the part of front end. So here to secure the system, we have added, I mean, we have then created a front end using Flash framework, which allows users to interact with the model. Flash help us to build the web interface for uploading images and showing the results. And to secure the system, we added a login system with the user authentication, storing user data in an SQLite database. And in the front end users, they will be able to upload images for detecting the objects. That given images will be pre-processed at the backend. It will be fed to the trained model, and then trained model will be detecting the small objects in the images. Coming to the algorithms used, so these are the various versions of the YOLO used in this project to detect the small objects. So for comparison, we have used YOLO V3, YOLO V5, YOLO V8, YOLO V9, that is YOLO V8 and YOLO by FPN. And this is the proposed model. Here are the extension models, that is YOLO V5S6, YOLO V5X6 and YOLO V9. So these are the algorithms used for detecting small objects. And to implement this project, we need basic requirements, which are hardware and software. Coming to hardware, we need operating system of Windows, processor of i5 and above, RAM of 8 GB and above, and hard disk of 25 GB and above. And coming to software, we need application of Anaconda, primary language of Python, front-end framework Flask, back-end framework Jupyter Notebook, database SQLite 3, and front-end technology that HTML, CSS, JavaScript, and Bootstrap 4. So this is the overview of the project. Now let us execute. To execute, we are supposed to open the code folder that contains source code files. So let's open the code folder. These are the source code files which are used in this project. So let us understand each of them. How will they impact the execution? So let's understand each of them. So here in the first folder, we have the dataset 1, and in the next folder, we have dataset 2. So let's see the dataset 1. Here, the images are stored in YOLOv5, YOLOv8, and YOLOv9. All the three folders has the same images. Reason for this, I will explain you after explaining YOLOv5 folder. Let's open this. So here, the dataset is split into three folders. One is train, test, and valid. Let's open the images which are in train folder. Here we have two more subfolders. One is images and labels. Let us open the images. So these are the images which has been used in this project for detecting small objects. So these are the images which are used to train the YOLOv5 model. So images which are in this folder we will be using to train the YOLOv5 model. Let's get back. And object locations. That means objects that we will be detecting at that locations are in this label file. So this label file contains the annotations or labels for the objects in the corresponding images in the image folder. Let's open this folder. So here each label file, it corresponds to an image file in the image folder. For example, this label file, it is correspondent to this image, and for this image, that is for the second image, it is correspondent to this label file. So these label files, they provide the object location. So it detects the objects in this, I mean locations of detected objects are in the label file. So similarly for all the 6,900 images, we have 6,900 in label files. So all this label files, they follow the YOLO format. Let's open a file for sample. Here, each line represents a detected object. How many lines we have in this file, that many objects are detected in that image. So here each line is followed by a bound of object class index, and that object class index is followed by bounding box coordinates. This is the object class index. This is x limit, this is y limit, this is width, and this is height. Here 3 is one type of object, 4 is one type of object, 6 is one type of object, 5 is one type of object, 0 is one type of object. Accordingly, we will be having many objects. So let's close this. Similarly, we will be having in all the other annotation files. Let's get back. And images which are in validation folder and test folder will be used for evaluating the trained model to see how well it is detecting on the unseen data. Let's get back. Same images we do have in YOLOv8 and YOLOv9 because each YOLO version requires specific type of annotations, different types of annotations. So because each YOLO version requires its own specific type of image and annotations for training and testing the models effectively, having separate folders helps keeping the dataset organized, ensuring that each YOLO version receives the correct annotations that it needs to function properly. So that is why they are annotated differently and saved in different folders. So dataset which is in this folder is used to train YOLOv8 model, and dataset which is in this folder is used to train YOLOv9 model. Similarly, in dataset 2, we have images in YOLOv5, YOLOv8, and YOLOv9. Here also data is split into train and validation. Let's open train folder. Here we have images and labels. Let's open images. So these are the images. So here are the images used to train the YOLOv5 model of the second dataset. And here we have label file for those images. Let's get back. And here in the sample folder, we have test cases that we will be using in the front end for detecting the small objects. This static folder, in this folder, we have files related to CSS, JavaScript, and Bootstrap files, which are important for the visual appeal. And then comes the templates folder. So this folder contains all the HTML pages used in this project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. And here in this app.py file, this .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in HTML templates. And here we have two Jupyter Notebook files. So these are the Jupyter Notebook files which contains combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. So in this notebook file, we will be loading the dataset 1 and training all the YOLO models. Accordingly, dataset 2 also. Coming to signup.db file, this file is a database file which is used to store the user information. And this is the model file. Now let's execute. So to execute, copy the path of the code folder from the address bar of the file explorer. I'm copying the path. Now open Anaconda prompt. It has been opened. Give the command cd, give the space, paste the copied path, and now click on enter. So here you can observe, right, current directory is changed to the code folders path. Now we are supposed to compile app.py file. So give the command python space app.py and now click on enter. This command will execute Python script and perform a runtime check for any syntax errors or logical issues. And after running the app.py file, Flask framework will host the application at local address, which is localhost, default address, which is localhost, and the port unless configured differently. So this is the localhost and this 5000 is the port. Now copy this local link provided by the Flask framework and paste it into any web browser. I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Paste the link here, click on enter. So this is the web page of the project, which is displayed in the browser, and this is developed using Flask framework. So we need to get registered first. Click on register and enter all the registration details if you are registering newly. I have already registered, so I'll directly sign in. Click on sign in. Give your username and the password. So I'm giving my username and the password. Now click on login. We have logged in successfully and we are redirected to detection page of the project. So here we are using two data sets, right? So that is why we will be doing detection for both the data sets. Let's do detection for data set 1. So under detection, click on data set 1. Here you can see a choose file button, right? We need to click on that for uploading the images. So click on choose file, open the sample folder, open the data set 1 because we are doing detection for the data set 1. So open that. So here are different images that now we will be using to detect detection purpose. Now let's upload this image. Click on open and now upload it. So this given image, it will be pre-processed at the backend and then it will be fed to the train model. Train model will be giving us the detection. So here we have the detection where two types of objects are detected, that is car and the truck. You can observe, right? Wherever there is a car, a bluish color bounding box is drawn around it with a 0.84 probability score. Probability score is nothing but that is the confidence level, that is how accurate the detection is in detecting that particular class. So here you can observe wherever there is truck, a bounding box is drawn around the truck and it is detected in green color bounding box. Accordingly, car also. Now let's get back and try with some more images. So now let's try with this image. Click on open and now upload it. Just wait for a while. File is being pre-processed at the backend. So here we got the detection. Here multiple detections we have. One car has been detected. So here four cars are detected. Multiple motors are detected in navy blue color bounding box. Pedestrians are detected in the pink color bounding box and people are detected in orange color bounding box. So you can observe, right? And oing tricycle is detected in bluish color bounding box. So here you can observe, right? We have multiple detections. Let's try with some more. Let's try uploading this image. Click on upload. So here we have the prediction that multiple pedestrians are detected. Motor is also detected. You can observe, right? All the pedestrians are detected in pink color bounding box and motor is detected in the blue color. Let's get back. Let's try with some more. Now let's upload this image. Now click on open. Click on upload. So here are the predictions, that is pedestrians are being predicted, car is predicted, and people are detected. Let's get back and try uploading some more images. So now let's upload. So let us upload this image. Click on open and now upload it. So here you can observe that car is detected, multiple cars are detected, and one truck is detected. Let's upload one more. So now let's upload this image where low light condition is there. It is in the images in the low light. So here we can observe that multiple cars are detected. Here you can observe, right? Cars are being detected. Let's upload one more image for this data set. So now let us upload this image. Click on open and now upload it. So here you can observe, right? A van has been detected, multiple cars are detected, and a tricycle is detected. You can observe, right? A tricycle is detected, and an oil tricycle is detected here. Let's get back. Now let's do detection with the dataset 2. Click on dataset 2 and click on choose file. Get back, open the dataset 2. So now we are supposed to upload these images for detection purpose. So now let's upload this image. Click on open and now upload it. So here also given image will be pre-processed at the backend. It will be fed to the train model and train model will be giving us the detections. So here there are two detections. Two are traffic signs and one is traffic light. Traffic light is detected in the pink color bounding box and traffic sign is red color. Let's get back. Click on choose file to upload some more. So now let's upload this image. So here you can observe, right? Multiple objects are detected. So vehicles are detected, traffic sign is detected, and traffic light is detected. Let us upload some more. So now let's upload this image. So here there are no objects, just we have the building. So that is why nothing has been detected. Let's try with some more. So now let us upload this image. So here multiple objects have been detected. That is traffic light and traffic signs are detected. You can observe, right? Traffic signs and traffic light are detected. Let's upload some more. So now let's upload this image. So here traffic sign and traffic lights are detected. So they are the objects present in this image. So they are detected because they are important for the autonomous vehicles to take the decision. Let's get back. So now let us upload this image. So here vehicles and traffic sign is detected. Let's get back. Now let's upload this one. So here vehicle and a traffic sign is detected. Let us upload 2 to 3 images more. So now let's upload this one. So here a person has been detected. You can observe, right? People. It is drawn in a white color bounding box. Let's upload some more. So now let's upload this one. So here you can observe, right? Multiple vehicles, traffic sign and traffic light has been detected. So this is how you need to execute the project. Now let us check with the graphs. Click on graph, click on dataset 1. So here the first graph which we have is the precision confidence curve graph of dataset 1, and here we have recall confidence curve graph. This is the F1 confidence, this is the confusion matrix, and this is the precision recall comparison graphs, and here is the mean average precision comparison graph. Here on x-axis we have accuracy score and on y-axis we have all the algorithms that are trained. So here accuracy, I mean precision, recall, and mean average precision are the error metrics used to evaluate all the detection models. So now let's check with the graphs of dataset 2. So here this is the precision confidence curve graph. This is the recall confidence curve graph. This is the FN confidence curve, confusion matrix, precision, recall, and FN score. So these are the graphs of the project. Now click on log out. In this way, just by uploading an image to the application, it will detect the small objects in the image. It will pinpoint the image, it will draw a bounding box, and it will specify what the object is. By this, autonomous vehicles, they can take the decision. So this is all about the project.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.